Yeah, thanks for the introduction and thanks for the organizing committee uh, to to give me this chance to present the talk here. This is a joint. The talk is based on a joint paper with a manual course. I was working on this called creative telescoping since 2007. I have been working on this for almost 10 years, and with manual we wrote a survey on these things. And instead of, and then we propose some problems in this paper. I will not list all the open problems, but I will talk about some of the problems. Let me give first a very brief introduction to the what is creative telescoping. Maybe some of them already know, but some of them maybe not. And then I will, in this method, actually there's a key notion so-called telescopers. Then I will talk about the three problems related to this operator, which is either a linear differential operator or linear recurrence operator or Q difference operator. So I will talk about some problem on this telescoper. So let me start from the brief introduction. In 1990s, and Doran Zerberger developed a very efficient algorithmic way to verify some combinatorial identities and also some identity involving integrals of special functions, such as this kind of binomial identity. Now we can use the computer app system immediately verify this. To give a proof of this kind of identities. Definitely you can give up combinatorial proof. And then you can also deal with more complicated things which involve some integrals and also some special functions. And this is Doran Delberger. Maybe you can try to prove this identity during my talk. And let me explain what is the creative telescope mean. First let me explain what the telescope mean. This is kind of a very classical thing. So you have a sequence and you would like to write this sequence as a difference of another sequence, which is both are in the same class, like F is rational, then G is also rational. Then we write this difference, that this is just a notation. And then you will curious about why we want to get this kind of thing. And this is like integrals. If you want to find the primitive of the integral function, then you get the evaluation of the sums. This is called the discrete version of a Newton-Leibniz formula. And for instance, in the high school, we know how to do this evaluation of this sum. And we write this summand as this difference, and then use this formula, you get the closed form. That's simple. But then you can go to more complicated things like hypergeometric sums, which is a summand involves some binomial coefficients, and then you can write this as the difference of something another, and then you get this closed form. This is still a binomial coefficient, is hypergeometric. And for this class of the hypergeometric terms, this problem, this telescopic problem, is completely solved by Bill Gosper in 1978, this paper. And he gave an algorithm which can test whether you, for a hypergeometric term, you can find another hypergeometric term such that this is true. And if there's no, and they also can decide. If this algorithm didn't find anything, then you can show that this cannot write as difference of another terms. And this problem is completely solved. Now, in general, a sequence cannot, even a hypergeometric terms, you cannot write as a difference of another hypergeometric terms. And then in this case, you should do something. If you have another extra parameter, like say n, and maybe you can do something with this n to make something creative telescoping. For instance, the idea, one of the options you can try to find a linear recurrence operator with polynomial coefficients, so that you apply this operator to this given maybe summand, and then you make it a telescoping sum. Telescoping this difference of another term. And then we call this operator, because this is a linear recurrence operator, we make this a telescoping, so we call this telescoper. Maybe it's different from the, but this some name actually has a meaning with some the real telescoper. But we call this G certificate for this operator. Let me see an example. For instance, you have these binomial coefficients in n and k, and then you can, for this function, actually the telescoper is first order. You can find the first order telescoper and the certificates of this form. And you will curious about why you do this. Somehow you need to give me a motivation. One of the motivation is prove, actually the computation for L and G is now there's an algorithm to do this. So this is a classical algorithm proposed by Doran Zerberger in 1991 or 1990 actually, and this is called the Zerberger algorithm, which will compute L and G for hypergeometric terms. Also, there are other algorithms for other class of functions. Let me explain why we do this kind of computation. I think the main motivation to prove such kind of combinatorial identities. So maybe this is a very easy example. So the idea, you want to prove this side equal to this side. And the idea is you first prove that both sides satisfy the same linear recurrence, and then you check some initial values. So let me first show that both sides satisfy a first order linear recurrence relation. So how to find this linear recurrence relation? You just run this creative telescoping algorithm. You can find, for this summand, you find this L and G. And this is the telescope and the certificate. And this is the first order. And then because, now we modify a little bit, because sum from 0 to n, it is equivalent to the minus infinity to plus infinity. And then this is the sum doing together with respect to k, and this operator commute with this operator. This is the operator in n. And then you commute it, and then you apply this operator on both sides of this equation, and then you do the use the commuter with this then. And then on the left-hand side, because this is already a difference of other things, and this is easy to use the discrete Newton-Leibniz formula, then you get this evaluation. And for many examples, for many identities, it turns out that this side is 0. And then what this mean? This means the left-hand side satisfies this linear recurrence relation. That is, just write down this one. And now we know that this side satisfies this linear recurrence relation. Then because usually for identity, this side is very nice, and then you just plug in this recurrence, and then you check that this also satisfies this linear recurrence. Then because first order, then you can check some initial value, then you can conclude that the identity is true. That's kind of basic idea. So that's why main computation step is this step, to compute L and G. And this seems very clear, not so complicated idea, but actually for many fairly complicated identity, you can use the same, prove this in this same way. And actually some people check that for many handbooks, 70% or a large amount of identity can be checked in this automatic way. That's powerful of the power of this idea. Okay, that's a brief introduction to creative telescoping. Definitely, as a mathematician, you will ask us following two fundamental problems. So there are different types of telescoper. Like for the combinatorial identity, this is a linear recurrence, and this side is difference. Then you can use this to prove these combinatorial identities. But usually, you can, for function which is involves continuous variable, you can also think about the linear differential operator. And then this side is derivative. And then this kind of things can be verified with some integral identities. And definitely there are some missed cases, like this side, the linear differential operator, this is different. And then this can be verified, this kind of power theory evaluation. Anyway, in general, this can be a linear differential or difference operator or some Q different operator. And this side may involve several sum of derivative or sum of a difference. I mean, this is in general is like this. And then for certain class of function, I think one of the basic question is how you can decide the existence of such kind of nice operator. They may not exist, so you need to first answer this kind of first mathematical question. And then once we know for certain class of function this kind of operator exists, and then sometimes doesn't mean you can it's not immediately get to an algorithm. Then you need to think about how to find design a good algorithm to compute this kind of operator, so that you can use for some applications. And then it turned out that to solve those two problems, and we need a lot of tools, like something from symbolic computation, and even use called the holonomic D module to guarantee some existence. And you definitely differential algebra is very useful. And also for functions, algebra function, you need some computational algebra geometry things. Okay, that's the tools. Let me start from the first question, which is about the existence. Let me state the question, which is not so complicated. Usually you will specify a class of function, say rational function, algebra function, or hypergeometric terms, or different something satisfied equation, or you can specify this class of function. And then you want to decide whether you need to propose some necessary and sufficient condition which you can check by algorithm, such that you can test the existence of such kind of operator. This may be partial, may be differential operator or difference operator or Q-difference operator. It depends on the problem. Okay, definitely the motivation to think about the existence, because there's some algorithm we check this first order, second order, or third order. If this operator doesn't exist, then the algorithm will not terminate. And this is important to show some algorithm terminates. So if you have this criteria, existing criteria. Another thing is coming from mathematics. So this is some useful for certain kind of hyper transcendence criteria. Let me show you two examples. The first one is done by Charlotte Hadouan and Michael Singer in 2008. And this is a very special case of their bigger theorem. So let me just say it in a simple way. So if you have a function satisfy this first order linear recurrence, for instance, like gamma function, and here is just x, x or something, 1 over x something. And then you want to prove this fx satisfies certain algebraic differential equation over rational function field. And then they show that if and only if this coefficient of the equation has a telescope of this form. So you see to check something is a transcendental, the algebraic dependent. And then you can reduce to the existence of this kind of telescope things. This is kind of linear problem, but this is the maybe non-linear problem. So sometimes this goes through the Galois theory. Another example is you can to verify some to check some algebraic dependence between some sums. You also need to reduce problem to the existence of telescope. For instance, if H is a hypergeometric terms in N, M, and K, and H is not of this form, and then the following sequence of sums, you see this, you take the sum, just shift a little bit with the first variable, and you get many sums, and then Carsten Schneider showed that those sums are algebraically independent over this rational function field if and only if this term has no telescope. So you need to check whether this term has telescope or not. This is so those things actually is about the transcendental criteria. And so now let's go to the status of the art of this problem on this problem. So in 1990, this Doran Zerberger using certain called holonomic D-module theory to show that a certain called a function if come from a holonomic sequence, and they show that for such kind of sequence, function always has the telescope. This is one of the sufficient condition for existence of telescope. And then later he give for a special class of this function, they present a more elementary proof in this paper. It's very long paper. And then, those two things are, holonomicity is just a sufficient condition. And until 2002, for rational function, Abramov and Ley give a sufficient and necessary condition, which you can check the existence of telescope for rational functions. And also this is extended to some other larger class, like hypergeometric terms, and also Q case. And in 2012 with Michael, actually we give, because there are different type of telescope, like many type I already show. And then for rational case, actually we give a very unified way to study this existing problem. And then later this was extended to deal with some other mixed case, which involves some continuous variable and discrete variable. So let me, and then actually for the moment, before 2015, all the result actually is only about the rational function in 2 variables. Until last year, we managed to extend the result to the rational function in 3 variables. Actually, it's fairly complicated. It seems not so. Okay, let me propose some. Present some open problems. There are 2 directions. One is you can go to more complicated function, or you can go to the more variables. For the moment, I only know the 3 variable in rational case. Let me go to the more complicated function. Like we know this elementary function, and there are very nice theory for the integration of elementary functions starting from the Liouville. And let me remind you what's the meaning of definition of elementary function. So f is a differential field, and f in an extension field of this k is called elementary over k if either f is algebraic, or f is exponential over k, or f is log over k. Definitely here exponential is defined by a first order, which means the f prime over f is in its derivative of the g. I mean, here expansion is not a meaning of analytical expansion. You can define this formally. And then an extension is elementary over K if this extension can be written in this form where this Ti is elementary over the previous extension. But this is called the elementary extension. And this is the way in calculus we build up the elementary function, which is just a formal way to say this. And then the natural question will be for the elementary function in two variables x and y over a rational function field, how you can decide whether there exists linear differential operator such that they satisfy this relation. Actually, you can show that not all elementary function has telescoper. For instance, like this example, this is a fairly simple example. Actually, we can prove that this has no telescoper with respect to y. So in general, I don't know how to have a nice criteria to decide the existence. We can also think about another question about elementary function. Let me define this called iterated integration of elementary function. So you have a differential field, and f is in this field, and we say that f is iteratively integrable in K if this, for any n, there is a Gn in this K such that this is true, which means you can integrate the f infinitely many times, still you get the things in K. This is kind of stable condition for f. And this kind of things actually has some connection with some problem in quantum field theory and also multiple zeta values. They have something application in those fields. You can see some paper by Ablinger, also Clemens, and I think they have a lot of paper about this topic. Okay, let me show you one simple fact. Just start from rational functions. If you have rational function, if this rational function is iteratively integrable, and then you can show that the only case is polynomial. Definitely you can integrate polynomial infinitely, anyway, that's hard to pronounce. Anyway, and then you can show that rational function, the only case is polynomial. And then we have, for the moment, we are working on this problem for the algebraic case. It seems very not so easy. We have some conjecture. Let's go to the algebraic case. This is the algebraic function in X, and we conjecture that this is iterated integrable if and only if f is this form, which is this form you can easily integrate infinite times because this is linear, and then you can always integrate this. And then we conjecture that actually that's the only possible case. That's one of the conjecture. There's also a second step of this. If you have a algebraic function, and then we conjecture that the following set actually is a Scholar-Mahler-Leher set, which means this is a union of a finite set and of finite many arithmetic progression. This reminds people maybe know this Scholar-Mahler-Leher theorem. So it's about the linear recurrence with constant coefficients. And we conjecture this may be true for this setting. I think Jason Bell, my colleague, I think with also Lu Yongfeng, he's here. I think we get the proof. I mean, at least Jason thinks maybe there's no gap. Maybe we need to still work a little bit about this. Seems very simple question, but actually the proof seems very complicated. Anyway, okay. Then the general problem is how you can characterize the class of elementary function so that they are iterated integrable inside the field of elementary function. So I don't know how to characterize this. I guess the only possible things will be sine, cosine, or something like this. Only simple function can appear to be iterated integrable. But I don't know how to find the criteria for this for the moment. Okay, let me go to another direction is multivariable case. So we think about the mixed hypergeometric terms. This is just a function in several continuous variables, so you can take a derivative. Several discrete variables, you can do the shifts. And then this function is a mixed hypergeometric term over rational function. It's just a generalization of rational function, but this is just take a derivative of the logarithm derivative of this function and then take the shift quotient. They are still rational function. Or in another word, it just means these are solution of system of first order homogeneous linear differential and differential equation. This is possible maybe one of the natural extension of a rational function. This is maybe more complicated, can be higher order. So definitely then you can ask the question is whether you can decide, solve the exist problem for this class of function. And this is the thing, just the restate of the creative telescoping. And then it turned out that when all the variable is continuous, and then we know that this function is always exist. This telescope always exists. But if there's some variable is discrete or some missing, then I don't know how to decide the existence. For the moment, we know some class. And then actually, to solve this problem, I think the first question will be to decide whether 1 is telescope or not. Whether 1 is telescope or not, which is the following question. It's just called the multivariate Gaussian algorithm, whether you can get this algorithm. This is just to decide whether 1 is telescope or not. Once you solve this problem, I think this is also related to another question which raised by George Andrew and Peter Pauli in 1994 in their GSC paper. They ask whether there's a possible to provide any algorithmic device to reduce multiple sum to single sum. Because once you write this in this difference form, then like n triple sum, you can be reduced to the n minus 1 triple sum. You can iterate this. Then maybe if you solve this problem, maybe you can answer partially of this question. But anyway, this is a very general question. There's also another very nice question, which is, I always ask people, maybe some people from algebra Germany, to solve this problem. This is a very old question. This is in a book by Picard and Simard about the algebra function in 2 variables. And at the end of this book, he proposed the following question. This is the French test. I just present it in English way. So to decide whether a rational function in 3 variables, x, y, z, you can rewrite whether you can decide this can be right in this form. And those PQ are still rational functions. So Picard himself solved the problem in the bivariable case. But in general, in this 3 variable case, I don't know. And I think there's one people called Philip Griffiths. He knows very well about this book. I sent an email to ask him, and things he says it seems not obvious. I don't know how to solve this problem also. This seems very simple question. Okay, let me go to the second part. It's about the construction of telescopes. In general, there's starting from 2090 to recently, there's 4 approach actually. I will not go through all the approach. The first approach usually is given by some people from algebra geometry, and also the second approach is based on the non-commutative elimination method. And then the third approach is based on some linear algebra linear system solving. And then I will focus on the fourth approach, which I developed since my PhD. So called the reduction-based approach. I will motivate this. So one of the motivations is the following. So for this this very simple rational function in 2 discrete variables n and k, and the telescope, we can show that telescope actually is this first order. And then I let you guess the size of certificate. This is like this. So, and then for many applications like combinatorial identity proving, you don't need these kind of big things. And then the natural question is, if you want to essentially improve the complexity of some algorithm, you need to try to avoid these big guys. And then how to do this? That's the question. So how you can separate the computation for telescope and the computation for certificate. There are many algorithms, many work has been done since 2010. So this is my first paper. We solved this kind of problem for rational functions using this classical method called Hamming reduction. So what's the Hamming reduction? This is very simple. So you have a rational function. The Hamming reduction will decompose this rational function into 2 parts. This part is already derivative of another rational function, and then this is a proper rational function with square-free denominator. And essentially, this is the Hamming reduction decompose an integral of rational function into 2 parts. One is rational part, one is logarithm part. This is transcendental part. So this is the Hamming reduction, and I use this to do the creative telescoping. And then I generalize this reduction to the more general case called hyperexpansion function. Then I designed a corresponding telescoping algorithm. And this is eventually go to the more general case and general and the difference case, and then to the algebraic function case. This is based on the Cheeger reduction. And then finally, in this year, I think the paper will appear, and we finally reach to the very general case called function defined case, which means a function satisfies a linear differential equation, but this equation has only regular singular points. That's a very general functions. Let me, maybe I have no much time, but let me skip this. This is the very simple idea how we can do these things for rational case. And let me skip it for the time. And then the further, then the natural question is how you can generalize this Hermit reduction to the general defined case. For the moment, we only know how to do this for the function case, and the non-function case, I don't know. And then this is just a precise statement of this problem. So you have a function which satisfies a linear differential equation with prime number coefficient, and you want to decompose function into two parts. And now one part is already derivative or something, and then this is a remaining part. But the remaining part is in a finite dimensional vector space. And also this, when this is called integrable, if our knowledge of this part is zero, this kind of certifying this integrability of f. And recently, I think Joris van der Hoeven claimed that he got some idea to prove to solve this problem. Still, there's some detail to be checked. So this is Joris' paper. And then also, once you get this Helm reduction, maybe it's natural to think about how you can develop a reduction-based telescope for these general defined functions. This is very general function. And I don't know. I don't say this is our final goal, but at least for the moment, it's nice to have this class, solve this class. And then let's go to the third part. Is about the inverse problem. This is like a Galois theory. You are given an equation, you compute the Galois group, and then the inverse problem usually give a group, and how you can decide this come from algebraic equation. And then the similar thing is here, like here. So now we know how for some class of function, you know how to compute this telescope, which is either a linear differential operator or linear recurrent operator. Then the question will, the inverse will be how you can characterize linear differential operator or recurrent operator that come from collinear telescoping. There's some special, many interesting class like rational function, algebraic function, or this is very, or defined function. For the moment, for this inverse problem, I only can answer the rational case. The theorem is the following. This is I get this theorem with Michael in 2012, 5 years ago. For a rational function, we can show that if a linear operator in the differential case is a minimum telescope, which means the order is minimum for some rational function, then we can show that this L actually is very special. This L, if defined a differential equation, has only algebraic solution, which means if you have a differential operator has transcendental solution, then this cannot become from can be a minimum telescope for a rational function. And in the difference case, we show that even stronger things. If this is come from telescoping or for rational function, then this defining recurrence equation has only rational solutions. So this is kind of answer this inverse problem in the rational case. Actually, we can say more. In general, this L also has very special factorization structure. If L is coming from a rational function, a minimum telescope for rational function, then L is so-called completely reduced, which means some, or in another word, is this L can be written as a left common, least common left multiple of some irreducible differential operators, which means this L is very simple. And for this kind of operator, it's very easy to factor this operator, which means in rational case, something you can say very more. And this completely solved the inverse problem for rational case. And now we are working on the algebraic case, seems something very complicated. I don't know how to extend this rational to those interesting class. Okay, if you are interested on more problems, please have a look at this paper. Thank you very much. Yeah, maybe more. Yes. Yeah, I think I'm more focused on this one, or for algebra functions like inverse problem for algebra function, also the iterated integration problem and involving algebra functions. Yeah, yeah, somehow. Thank you.